Okay, welcome in the second session in this week. One more thing. Okay, I think, oh, my screen is, okay, I think now we can start. Okay, that means this is the second session in week 7, and just a quick notes, quick announcement. This is the last week before the second midterm. That means next week will be the review, and then the test will be open on Thursday. And I hope by now everyone has an examity appointment booked, because booking at the last minute is not really recommended, of course, and it is stressful. Okay? Another thing is, I will release, if I just the recommendation for you, I will really start practicing for your midterm, looking at the module 8, the exam 2 week. We did post lots of sample tests. That means what I will do, I will print the sample test, just the blank test, don't look at the solution. Print the sample test, try to lock yourself in the nice, clean and empty room, okay? Time yourself, that means put the time, 90 minutes, and having like no notes, no books, no electronics in the room, try to solve the test. Okay? That means creating a real examination time, examination settings, environment, and taking the test without any breaks, just straight 90 minutes. Then the result of the test is really the true knowledge, will show your readiness. Okay? I think I said this a few times, but I will really recommend you to do this. Okay? And then, of course, you can check against the solution. The solutions are provided on Canvas. Okay? You can correct your mistakes eventually, and then you can take another test. And I think we have 5 or 6 of them. And I can guarantee, if you will create the real examination settings environment, and then if you will take the test, and whatever the score you will get the same score on your actual test. Okay? Because if you will understand all of the concepts which are on that sample test, you're definitely ready for your actual test. Okay? That means please try to create these settings and take the test this way. Okay? On my laptop is something is going on. Okay, hopefully now will be good. Okay, that means that's just my quick announcement. Make sure that you have examity appointment booked for your second test, and try to practice, even starting today. Okay, because we almost done with the whole concept, the whole material for the test too. Okay. That's what we have. We still in chapter 11, of course, and we do have section 11.6 and 11.7, but 11.7 is just a summary of all of the tests, which you probably saw on Canvas. I did post like a nice list of all of the tests. I did print. That's me, I'm just showing you all of the tests and kind of like the way that you can use them. Also on the discussion board, I think you can also see like the small suggestion, like what to even like start with. If you have an infinite series, how can you start testing? Okay? Of course, we have to start with the test for divergence, and maybe check if it's the geometric one or telescopic one, P-series test, and then maybe if all of the terms are positive, you may use the comparison test. If not, the alternating series test. Okay, and then today I will try to show you the last 2 tests, which is the ratio test and the root test. Okay? And they probably, when you will see them at first, they look like quite time consuming, but I can tell you they are most favorite tests. Okay, because they are nice, like we can nice compute and we can nicely see the output, the conclusion. Okay, that means let's start. That means what we will talk today. We still have to determine whether the series is convergent or divergent, but what we're adding the absolute convergence. Okay, that means what this means. This simply means that if we have a given series, and the series A sub n, And if I will take the absolute value of the terms, yes, we can see the absolute value of the terms, okay, then of course all of them becomes positive. And if I will test this for convergence, that means taking the absolute value and testing the convergence, and if the infinite series is convergent, then I can call that is absolutely convergent. Okay, that means this is the definition. The series A sub n is called absolutely convergent if the series of the absolute value is convergent. I will switch off my camera. Okay, I'm still there, but then you can see the full screen. Okay, that means one more time. We will call the series absolutely convergent if the series of absolute value is convergent. That means that sounds easy, right? Sounds quite obvious. One thing that you may notice, if all of the terms of the infinite series are positive, then we're not even changing anything, because absolute value of the positive term is still positive, is still the same number. Okay, that means absolute convergence will be exactly the same like the convergence. Okay, that means let's see what we have. For example, taking the alternating series, -1 to the n minus 1 over n squared. We do have a terms 1, minus 1/4, plus 1/9, minus 1 over 16, and so on. Okay? That means this is definitely absolutely convergent because I did the work for you. If I take absolute value, okay, let's see what's changed. The negative part, I mean negative positive, the alternating part on the top will become just positive, just 1. Because on the top, in the numerator, we have -1, +1, -1, +1. Taking absolute value of it, all of the terms becomes 1, positive. Okay? N squared is always positive. That's we can see I'm not changing anything. That means taking the absolute value of this infinite series, I am actually getting this. And 1 over n squared, everybody knows by the p-series test, that is convergent. Okay? That means this is the absolute value. Then I can say my original series is absolutely convergent. Okay, nice and easy. Oh, something is, okay, hopefully everything will be good with my laptop. Okay, so now let's see this, okay? That means now let's see what's happened with alternating harmonic series, okay? We know that it's convergent. Yeah? We know, first of all, we know that the harmonic one, just 1 over n, okay? Yeah, that's harmonic, right? That means this is definitely divergent. We remember, yes, just 1 over n. It's definitely the harmonic series is divergent. Okay, divergent. But we also learned, probably yesterday, because that was the section 11.5, the alternating series test, we learned that the alternating harmonic series is convergent. Okay, because we remember, as soon as we see the formula with the part -1 to the power of n or n minus 1, we know that is alternating series. Then we can try to use the alternating series test. And what we're doing, we're pulling out the positive part, which the main formula, we will call b sub n, is 1 over n. And then we're testing this formula must be positive. Limit of b sub n at infinity must be 0, and it is 0. And of course, b sub n is decreasing, but it is decreasing. All of the other terms, I mean, all of the next terms, 1/2, 1/3, 1/4, they're getting smaller, decreasing. That means as soon as we satisfied all of this condition, of course, having an alternating part, we can call that this infinite alternating series is convergent by AST. By AST. And I did this for you. That's just probably the same thing you had yesterday. I'm just repeating, but I would like to point the difference. Can you see this corner? 1 over n, and it's no question, it's just divergent. I'm kind of using the same formula for this one, right? 1 over n, but please note the difference. This one, I am applying the alternating series test, and I'm testing the part of the formula, because the other part was alternating one. This one is just purely direct formula, 1 over n, no alternating. That means I'm not even using this. I'm not even allowed to use this test. Okay? That means we know, of course, we know that this is harmonic series divergent, but that's what I'm saying. Do not, because sometimes you will tell me, oh, 1 over n, and you can say, oh, it's positive, limit 0, decreasing, it's convergent. But no. We can't use this hypothesis, this point, if we don't have -1 part, -1 to the n. Okay, that's the difference. Okay, but now what is our topic today? The topic today is the absolute convergence. Having this formula, I will take the absolute value. Okay. Okay, let me just move my laptop. Okay, that's me taking the absolute value. We remember what's happened. N is positive, that means N will stay, okay, like it is, but the -1, +1 becomes 1. And let's see what we've got. We actually got the normal harmonic series, and of course is divergent. That means what is the conclusion? I did highlight the conclusion. The alternating harmonic series, which is convergent, is not absolutely convergent, because the absolute value gave me divergence. Okay? That's mean what we also have, because the mathematician, sometimes they don't like leaving like things like undefined. That means since this is not absolutely convergent, however, the original series was convergent, we will call that this type of series is conditionally convergent. Okay, like under certain condition. That means, let's read the definition. A series A sub n is called conditionally convergent if it is convergent at first, like the original one, but it's not absolutely convergent. Okay, that's actually the example of the previous slide, the alternating harmonic one, because originally it is convergent with the alternating part, but when I remove this by taking absolute value of it, I'm making divergence. That means it's not absolutely convergent. Okay, that means now the main question will be testing the absolute convergence and conditional convergence. Okay. Let's see, and sometimes we will call absolute convergence like AC and conditional convergence like CC, conditionally convergent. Okay, let's see what we have. Okay, I have the next example, the infinite series, -1 to the n, n squared over n to the power of 4 plus 1. Okay, that's what I see. I see -1 to the n. That means so far I will test right away. This series by using AST, because I see the -1 to the n. But however, because I didn't type my question, but I'm asking if this is absolutely convergent or conditionally convergent. Right? That means or divergent. Of course, if it's not divergent at all. But what I will do, I will start with absolute value. That means taking the absolute value, I am changing things, and my infinite sum will be -1 to the n becomes +1. That means only n squared stays the same, and n to the power of 4 plus 1 also stays the same. Okay, that means now we can see no alternating part. Now I can take care of this. And actually, maybe you can tell me, what test shall I use to test this, to test of this formula? What do you think? Based on the previous section, 11.2, 11.3, 11.4, 5. 11.5 was the alternating one. That means it's no alternating anymore. Yeah, that's the thing, AST, we can't use AST anymore. I can use AST for the original one. Oh yes, I can definitely use AST. Okay? Yes, Odalis, thank you. I think I can nicely compare, because the comparison is always so nice and easy. That means I can keep the formula, I can keep n squared, and I can keep n to the power of 4. That means, because we remember we're only looking at the leading function terms. And since the denominator is bigger on this one, the whole fraction is smaller. That means respectively the series has the same relation. And this one, if I will simplify, nice and easy, 1 over n squared. And by the p-series test, p is 2 greater than 1, it's definitely convergent. And that means this is convergent. Everything what is smaller is also convergent. Okay, that means this is convergent by direct comparison test. Okay, and I did compare with 1 over n squared. Okay, but however, I am testing the absolute convergence. That means my original series is absolutely convergent. Absolutely convergent. And that means I can delete this one. Okay, but now what I can also tell you, let me, because what is also really important, okay? If, because the absolute value is quite strong mathematical operation. That means now for the infinite series, if the infinite series is absolutely convergent, is also convergent. That means it's no other option that we will get conditional convergent or divergence. That means now, if I will remove my absolute value, and if I would like to test this formula, not taking absolute value, but having the original form and using AST, I will also get convergence. And how do I know this? Because I've got absolute convergence. That means if the infinite series is absolutely convergent, it's also convergent. And that means this also like concludes the convergence. Okay, let's do more problems. Okay, that means now I will show you, yes, the next property, that the absolute convergence implies the convergence. That's what I just said. Okay, that we can just actually what I just said. Okay, that means that if the infinite series is absolutely convergent, it's just convergent. Okay, this means that even not taking the absolute value, the original formula was convergent. Of course, if it's not absolutely convergent, then I have problem, because then I have to double check the original formula could be convergent, then the case is for conditional convergence, or if the original formula was divergent, it's just divergent. Okay? But absolute convergence always tell me convergence. And sometimes, even I can come back to my slide, we can see sometimes it's much, much easier to take the absolute value, right, and look, yes, and do the absolute convergence. Because as again, if I will go through the AST, I can do this. Because AST is telling me that I have to pull out again, let me write here, my positive part, which is just n squared over n to the power of 4 plus 1. And this formula must be positive. Limit at infinity is 0. And we can see is 0 because denominator is greater. And then b sub n is definitely decreasing. Decreasing. And that means check, check, and check. Of course, we kind of know this. This is obvious that is positive, but maybe limit, we need few times to think that limit is 0, and we need even like few minutes to prove decreasing. maybe through the derivative way. Right? That means it's not easy to just check everything so fast. But we know that this is definitely true. And I can say this is convergent by AST. Convergent by alternating series test. Okay, we have the proof. But as I said, the blue part is time consuming. You can always start with the absolute convergence, do the comparison, for example, like we did now, and get, I mean, it is absolutely convergent. Also, this concludes convergence. Okay, that's just for you the extra tool. That's quite important. Okay, and now let's look at something like that. Determine whether this series is convergent or divergent. The summation from 1 to infinity cosine of n over n squared. Okay, that we can see. If I will expand this, cosine of 1 over 1 squared, cosine of 2 over 2 squared, and so on. But what is the weird thing about this? The weird thing is that the cosine values, cosine of 2, cosine of, of 1, 2, 3, 4, they are not always positive. Okay? Like, because cosine function, I can draw maybe, yeah, looks like that. That means a few values, yeah, like cosine of 1, cosine of 2, cosine of 3, cosine of 4, 5. I don't know exactly because I have to change for the radians. But we can see the blue dots. That's the cosine values. That means some of the values are positive and then few negative, positive, negative. That's we do have problem. We not even have the alternating one because they not alternate like positive, negative, positive. No, they are like a few positive, few negatives. Few positive, few negatives. That's we do have problem. We can't use AST. We can't use comparison right away because also we remember comparison test is only if all of the terms are positive. Okay, that means what we can do. Oh, okay, I can write the solution. We can try with absolute convergence. That means I will try to take this infinite series and I will change the formula for absolute convergence. That means what I have. N squared is not changing, but cosine of n, I think I have to keep it absolute value. Okay? Because this is showing me that all of the terms are positive now. Okay? At least that's actually quite helpful information. Because since all of the terms are positive, I might use comparison because cosine sine is really good for the comparison. I will use comparison. I will keep n squared, but the maximum value, what is the maximum value of cosine? I can ask you. What's the maximum value of cosine function for any angle? 1, yes, thank you. That means 1 is the maximum value. All of the others are less or equal to. That we can see. I did create nice relation. I have the series 1 over n squared. Again, everybody knows that this is convergent by the P test. Convergent, and everything what is smaller, it's convergent too. Convergent by direct comparison test, and we did compare with this. Okay, but please note, without absolute value on that cosine, this will be wrong. We can't say convergent just because like that. That means normally I can say this is absolutely convergent, and of course this implies convergent. And that means it's much better and safe to say it's absolutely convergent, and then everybody knows that it's convergent too. Okay, that means this is the nice example that's showing us that absolute convergence is so helpful. Okay. See, yeah, I did the same comparison. Okay, that's what I have on my next slide. As promised, as the title promise, we do have the last 2 tests, okay? And the first one is the ratio test, and the last one is the root test. That means let's see what we will do. Having the infinite series, right? The summation of a sub n from 1 to infinity. What we can do, using the ratio test, we will get the conclusion, like, doing a certain things, which I can explain, like computing some limits, we will get the nice conclusion, because the ratio test will test absolute convergence right away. That means now, when we will apply the ratio test, okay, and if we will get the conclusion that is telling me, actually, I can maybe explain what we will do. Applying the ratio test, we will compute a limit of the ratio. Okay? That means having a formula a sub n, I have to create the ratio of a sub n plus 1 over a sub n. That means we all understand what a sub n plus 1 means. It's just the next term of the sequence, a sub n. Okay? That means I will create this one. It's relatively easy because instead of n in the formula, I will put n plus 1. And then ready. That means this will be my numerator. Then I have to divide by the original formula, a sub n. Creating this ratio, I will compute a limit, how this ratio behaves at infinity. And if I will get a number less than 1, okay, the number less than 1, okay, then I can say right away that this infinite series is absolutely convergent, which of course concludes convergence too. Okay, that's what I say. It's quite helpful. Okay? And of course, it's absolute value. That means everything will be positive, but we have to take absolute value. Okay, that means number less than 1. However, if we will compute the same limit of the same ratio, and if the answer is greater than 1 or infinity, which theoretically is also greater than 1, then we can say the infinite series is divergent. And another important note, we don't have to check for conditional convergence. It's no option, no way that we will get conditional convergence. Because testing this limit and getting the numbers like greater than 1 or infinity, I would say absolute divergence. It's divergent. Okay? The infinite series is divergent. Okay? The only thing is, if we will get 1, this means that the ratio test doesn't work. It's inconclusive. That means we have to just find different tests. We know that some of the tests are not working, okay, for the certain formulas. That means 1 is not good. 1 is definitely not good. Okay? That we can see how nice, because I can tell you computing this ratio and the limit is quite fun, quite nice job to do. And then you will look at the number. Oh, less than 1, absolutely convergent. Greater than 1, divergent. Okay? But please note, we don't have to be worried for the conditionally convergent or something. No, this test is not testing this. Okay? Of course, if the test doesn't work, then probably we have some issue, and then maybe we will get conditional convergence. But at first, we have to find different tool, different test. Okay? That means let's see. For example, this one. One thing that I would like to mention to the ratio test, because you will probably ask me like, how do we know, having the infinite series, how do I know that I can use the ratio test? The one suggestion is, if you will see the formula for a sub n, and I can switch for my next slide, like this one, that's my a sub n, okay? If you will see the formula, that this formula contains a few different types of expression. That means, for example, I see n cubed, which is the power function. I see 3 to the n, which is the exponential function. And of course, I see this alternating part, but that's also okay. But at least this one, power function, exponential function. I see 2 different types of like functions, expressions. Then I will think right away, oh, I think ratio test is good. If you will see only one function, probably the ratio test will not work. You can always check, but probably we will get 1. But at least 2 different, we can even have 3 different formulas, 3 different types of formulas. Even better, it will be good for the ratio test. Okay, that means let's see what we need. Our a sub n formula is negative 1 to the n cubed, and 3 to the n. Okay? Then what I need a sub n plus 1. Instead of n, I will put n plus 1. That means this will be n plus 1. N cube will give me n plus 1 cube. And then 3 to the n, I will put n plus 1. Okay? One thing that I can simplify probably right away, because applying a ratio test, I have to compute a limit at infinity of the ratio a sub n plus 1 over a sub n, an absolute value. Okay? That means I can probably do this right away. Taking the absolute value, what I will do? I will simply miss the negative 1. That means this will be n cubed over 3 to the n. And this one, I can write here. If I will apply the absolute value, I will miss the negative 1 to the n plus 1. I will have n plus 1 cubed, and I will have 3 to the n plus 1. And as we can see, then I can at least make my fraction a little bit simple. I will skip this negative 1. And the rest of the terms are positive. Okay, that means let's see. Because both of them are fractions, that means what I can do, I can copy a sub n plus 1, and dividing by fraction means multiplying by the reciprocal. Okay, I can keep absolute value for now. That means I will copy for my limit at infinity, I will copy my term a sub n plus 1. That means n plus 1 cube, 3 to the power of n plus 1, and times, and I will flip a sub n, 3 to the power of n cube. And okay, I will put the absolute value, but we don't have to. All of the terms are positive. That's what I did with the blue one. Okay, and now we have to simplify. Let's try to compute this limit. Maybe you know the answer, but what we have? We have n plus 1 cube, we have 3 to the n. 3 to the power of n plus 1 means 3 to the power of n times 3 to the power of 1. Okay, and then n cube. And what I can cancel out? I can cancel out at least this. Okay, nice. I did cancel one of the function. And what I have n plus 1 cube, the third degree, and I have 3n cube. Okay, who can tell me what is this limit? At infinity. We do have n cube and 3n cube. Do you remember? If the degree is the same of the polynomials from the top and the bottom, we're just taking the ratio of the leading coefficient. Yes, Rin, thank you, Kyrie, yeah, thank you. 1/3, excellent. And 1/3 is a beautiful number, less than 1, okay? That means we do have absolute convergence. This is absolutely convergent by ratio test. Yeah, we can see, let me divide my screen. We're just looking at this limit. And I can tell you, doing all of this simplification is a nice job, okay? Okay, absolute convergence. Okay, let's look at my next example. Oh, okay. Test the series for absolute convergence. And the formula is, of course, the summation from 1 to infinity, 100 to the power of n over n factorial. That means definitely good for the ratio test, because I see the power function, okay, like 100 to the power of n, and I see factorial. Do you remember from section 11.1 the factorials? Everybody is understanding the factorials? Oh, you can answer. Okay, like just, I think what you can do, you can check, I did put like a really short video about the factorials, which is on Canvas. You can probably check it after, okay? But I can just explain you that factorial means the product, like n factorials, means the product of all of the positive integers less than or equal to n. That means n factorial means 1 times 2 times 3, and then times n. N is the last number. And that means just Just things like that. And let's say 1 factorial will be just 1. 2 factorial will be 1 times 2. 3 factorial will be 1 times 2 times 3. Of course, this is 6, okay? 4 factorial is 1 times 2 times 3 times 4. Ooh, 6 times 4, 24, and so on, right? That we can see that's the way to compute the factorial. But please note one thing. Yeah, it's actually nice property. I mean, another like type of function. Okay, let's look at this. Like 4 factorial is defined as a 1 times 2 times 3 times 4. But taking 1 times 2 times 3, I can rewrite that this is 3 factorial times 4. Okay, that means 4 factorial is definitely 3 factorial times 4. Yeah, really nice. Or even general, n factorial, I can rewrite as a 1 number less. We can see 4, 3. 3 is 1 number less. N minus 1 factorial and times n, because I always have to end with that number. Okay, makes sense? This expression is the same like this one. All right. Okay, that means n factorial can be always rewrite as a 1 number less n minus 1 factorial times n, no factorial. Okay. Or I can even move, let's see this one. I can even say 2 factorial times 3, this is exclamation mark, 2 factorial, my writing gets sloppy, 2 factorial times 3 times 4. Right? The same thing. That means I can like subtract 2 numbers and then I still have to fill in all of my integers. 3, 4. 4 is the last one. That means n factorial, I can rewrite as a n minus 2 factorial and then n minus 1 times n. Okay? Because we will need some of this simplification. Okay? That means that's pretty much everything what we have to know about the factorial. And one thing, it's always, I can use this one because what we also have 0 factorial. Do you think what is 0 factorial? Maybe you heard something. I can prove it, probably even using this blue box. Yes, 0. What we do have in mathematics something like we call empty products. Okay, and of course, if I don't want to go like deeper in this factorial because in the probability for the permutation we use factorials and it's nice to prove. But what I can do, I can get that number using this blue box. That means let's in that blue box, because this is definitely true statement. Yeah, I will substitute for n1. That means let's see what we will get. Okay, I'm substituting for n1. 1 factorial, and then 1 minus 1 factorial times 1. Okay? 1, 1, 1. Okay, 1 factorial, and 1 minus 1 is a 0 factorial times 1. 1 factorial is 1. 0 factorial times 1 is just 0 factorial. That means, can you see what we've got? What is 0 factorial? Yeah, you can say it's simply 1. I know, sounds probably weird, okay? But that's what I said, yes. It's nice, and this is nice proof. 0 factorial is 1. If somebody will ask you, you can prove it. Yeah? Like the same like taking a number to the power of 0, we all know that is always 1. That means that's kind of like this empty products, we call it. Okay, that means you know the factorials. Let's come back to our series. I don't know if I have enough room, but possibly. That means we just learned that it's good to use the ratio test because we have 2 different types of formula. That means I will use a ratio. Okay, ratio test. Actually, I also, what I have to also do, I kind of like forgot because of course I'm so focusing on the topic, but please remember always check the test for divergence, because we know what is test for divergence. We're looking at the formula, and as soon as this formula, this a sub n, at infinity, if this is not 0, then we're done. Then we have no chance for convergence. Okay? But of course, this limit is 0 because factorial grows much, much faster than the exponential function. That means this is definitely 0. Okay, but please remember, I even kind of lost my like attention to this test for divergence because I really want to use the ratio test, and we have to use the ratio test. But just to tell you that this, even if we have two formulas, you can always check the limit. If the limit is not 0, no chance for convergence. But if the limit is 0, we know nothing, right? We remember we know nothing about convergence. Then we have to open our toolbox and pick a tool, pick a test. Okay, ratio test. That's mean what I need. I need a sub n, which is just this, okay? And I will need the next one, a sub n plus 1, 100 to the power of n plus 1, and n plus 1 factorial. Okay, now the ratio. Okay, limit as n goes to the infinity, a sub n plus 1 over a sub n. I can skip absolute value because all of the terms are positive. That means limit as n goes to the infinity, a sub n plus 1 is my second formula. That means 100 n plus 1 over n plus 1 factorial. And times, and I will flip the a sub n. Dividing by fraction means multiplying by the reciprocal. N factorial, 100 to the n. Okay. Limit as n goes to the infinity, 100 to the power of n plus 1 is 100 to the power of n times 100 to the power of 1. And then I do have 100 to the power of n, which I will cancel out. But now what I have n factorial and n plus 1 factorial. We really have to simplify this because we have to remove these factorials. That's mean what we will do. Always looking at these factorials, having n and n plus 1, I always have to pick the number which is greater. Okay, greater. That means I will keep n factorial because it's smaller, and now this number is greater. That means I can subtract 1 because we can see the difference is 1. That means I'm subtracting 1 from n plus 1 and I'm getting n. This will be factorial, and then I have to fill out up to n plus 1. Like, do you remember, like I did with this one? I did subtract 2 or even 1, let's say this one. That means I did subtract 1, n minus 1, factorial, and then n. It's something like, okay, n plus 1. Let me say 8 factorials over, oh no, one more, 9 factorial. Okay, that means I will keep the smaller value, and from 1 bigger, I will subtract 1, which will be 8 factorial, and then times 9. And you see, I did subtract 1, which is just n, and times n plus 1. Okay, makes sense. You can definitely check my video from about the factorials, okay, and you will get more confidence. Okay, I will erase this because I need space, and then hang on, I just need nice division. Okay, and what I can do? Let me pick different color. N factorial, 100 to the n, 100 to the n. Okay, that's me. What is my limit? Limit at infinity, 100 over n plus 1. Okay, who can tell me this limit? Just 100, which is not even n. That means 100 over big numbers, of course, is small number. And 0 is a good number because 0 is less than 1. Okay? 0 is also a good number. That's when we do have absolute convergence by ratio test. Okay? That means the infinite series is absolutely convergent by the ratio test. Okay? Nice. Let's look at the next one. Oh, okay. Just this one. 1 over n factorial. what I have next. Oh, I have this one. Oh, okay, I have 3 more. Okay, let's see, we can even solve all of them because will be excellent practice for your quizzes and of course the exam too. Okay, 1 over n factorial. That means you can probably think, oh, can we really use the ratio test? Because I said that the ratio test is really good when we have like a mixture of different types of formulas, and suddenly we just see n factorial, just one type. But I can also add, of course, that's the reason that I have this example for you. I can also add to this the note that if we have one type of expression, and if this expression is factorial, you can also try the ratio test. Because we kind of learned on the previous slide how to simplify. That's what we will get some rational function that is easy to get the limit. And we will probably not get one. Okay? I mean, if we will get one, because of the other parts, we can always skip the test and find another test. But I can definitely say that we can try the ratio test if we see factorial only. Okay? That means I will try. You can probably think that this is convergent, but I will not guess. Okay? I will still apply the test, ratio test. That means we need a sub n, which is just this, and we need a sub n plus 1. Just n plus 1 factorial. And the ratio test, I have to find, I'm trying to organize my page. Limit as n goes to the infinity of the ratio, a sub n plus 1 over a sub n. I can skip the absolute value because all of the terms are positive. Okay, let me actually write the huge fraction. A sub n plus 1 over a sub n. But dividing by fraction means multiplying by the reciprocal. That means I will have 1 over n plus 1 factorial, and multiplying by the reciprocal, I will have times n factorial. Okay, and now let's practice how we can simplify. Okay, I do have n and n plus 1. The same situation like the previous problem. That means n is the smaller one, I will keep this one, and the bigger number, I can subtract 1, which I will get just n factorial, and then I have to finish with n plus 1. Because the factorial is the product with all of the numbers less than equal to n plus 1. This number must be the last one. Okay, nicely, factorial is gone. And can you tell me what is this limit? Limit at infinity 1 over n plus 1. Who can tell me? Oh, come on, we do have some participants. No, you're not there. I know that you're there. 0. Thank you for standing up for the whole class. Thank you. I don't know if I can read the name. Okay, I don't know, but okay, thank you. Okay, and 0 is a good number, it's less than 1. That means this is absolutely convergent by the ratio test. Because that's the conclusion. I can write. Okay, I can split my side. Okay, let's do 2 more, and then I will show you the last test. Okay, oh, okay, you asking me. Actually, I know that because Dr. Bank is sending these emails, and I don't know if he make this adjustment. But yes, sometimes my class will be the evening class, 9 p.m. But I know that some students also think that it's too late, and I'm trying to like accommodate. Of course, I can't accommodate everyone, but I'm trying to balance. That means I'm okay with the 9 o'clock in the evening, or I'm also okay with the midday 12. That means I can keep the 12 if you like. Do you like the 12 o'clock, or you prefer the evening class? Because as soon as you get email from me, this will be the real time that I will tell you. I can double check with the Dr. Bank, because I'm always telling him that to adjust my time, but probably he kind of forgot that sometimes the class could be at 12. Okay. Yeah, okay, yeah, that's what I'm always, yes, that's what I'm always getting the message from students. I don't mind, could be the 12, could be the midday, or could be the 9 o'clock. But I also don't mind. I'm happy to, of course, I will do everything for my students to accommodate and to do whatever is good for you. Okay? And I know that lots of students are watching later. That means it doesn't really matter if it's 9 p.m. or 12. But of course, it's nice to attend the live session, yes, and to answer my questions, and I see your names. That means it's always nice. Okay, I can keep the 12. If you really don't like, please email me or please put on the discussion board, okay? Because as soon as I will get some feedback and some like asking for different time, I will definitely change the time, okay? But yeah, 12 o'clock, I think it's good. Of course, if we have time, we can think better during the day, yes, rather than the evening. Okay, that means I always watch my emails, okay? I will always send you an announcement and the email, what time will be my Wednesday session. Okay, let's keep working. Okay, that means now we have n to the power of n over n factorial. That means this is definitely a combination of, this is the combination of different types of formulas. That means ratio test will work. Okay, let's see. Ratio test. What I need a sub. Let me organize because we'll be a little bit longer. A sub n, of course, is just this, n to the n factorial. A sub n plus 1 is n plus 1 to the power of n plus 1, and then n plus 1 factorial. Okay, and let's create a ratio and compute a limit of infinity. A sub n plus 1 over a sub n absolute value. But all of the terms are positive. I'm not worried for the absolute value. Okay, limit as n goes to infinity. That means I have to copy this n plus 1 to the power of n plus 1 over n plus 1 factorial and times, and I will flip a sub n factorial, n to the n. Okay, let me put this, but we don't have to. Okay, that's what we have. N plus 1 to the power of n times n plus 1 to the power of 1, which I don't even have to put 1. And then I have n to the n. And now the same thing, n factorial and n plus 1. N plus 1 is bigger, that means n plus 1 factorial, I will rewrite as one number less, which is n factorial, times the last one, n plus 1, without the factorial. And then n factorial. And let's see what we can do. We can simplify this, and this is n plus 1, and this is n plus 1. Okay, that means one of the power function is simplified. Okay, that means what we have. We do have n plus 1 to the power of n, and we have n to the power of n. I think I can combine the numbers because the power is the same, n plus 1 over n to the power of n. Okay, and then, oh, interesting, I can say n over n is 1, and 1 over n will stay 1 over n. Okay, and who remembers this limit? Do you remember this limit? Actually, that was the reason that I solved this one. And I can show on this slide. But who remembers this limit from my section about 11.1 sequences? And I was solving the sequences and was quite late because I think that was the evening session. And I said, okay, let's solve one more sequence. Let's solve the limit. Let's check how 1 plus 1 over n to the power of n behaves. And who watched that section? Who watched that video? Do you remember this limit? Because of course, what we have, we do have an expression, if n is infinity, we do have 1 over 0 is 1 over infinity is 0, 1 over big number is 0, and then n is infinity. That we do have 1 to the power of infinity. This is indeterminate form. That means it's a long process to solve this one because we have to change for the exponential form. We have to apply the L'Hopital rule and so on. Okay? But I can tell you, and I don't want you to forget, this limit is e. Okay, that's how the number e is defined. Icon box. Please do not miss that. Okay, even on your test. That means if you will see 1 plus 1 over n to the power of n at infinity, this expression is e. Okay? And actually, getting back to our ratio test, do you know the e value is less than 1 or greater than 1? Oh, of course it's greater than 1. That means this is greater than 1. The infinite series is divergent. Divergent by a ratio test. Okay? Yeah, it's worth to watch all of the videos. Okay? That means it's divergent by the ratio test. Okay? And actually also, as I said 5 minutes ago, it is worth to look at the formula and apply the test for divergence. However, we will not know, but I can tell you the relative growing rate, the function n to the power of n, or if we can think x to the power of x, is much, much faster than n factorial. Even the n factorial is fast, but this is much, much faster. That's the reason that this limit is infinity. That means probably not even computing everything, we will tell right away that it's divergent by the test for divergence. We can also say this, divergent by test for divergence, because this limit of this is infinity. Okay, it's going to the infinity. Okay, I will, no, I don't want to remove everything. Okay, but again, I still have the reason to apply the ratio test because of that limit. Okay, I mean, nice simplification, but this limit, yeah, please remember that limit is just e. Okay, and I have one more. Okay, that means this one is, okay, this one has tricky part because has 2n factorial. That means just one thing will be different. And speaking about the test for divergence, I think the factorial grows much, much faster. That means the whole limit will be 0. Okay, that means if it's 0, it's not divergent right away, but at least we do have chance for convergence. Okay, that means let's apply the ratio test definitely. We have power function, we have exponential function and factorial function. 3 different types of expression. Okay, let's see. A sub n, actually absolute value will be just n squared, 2 to the n, 2n factorial. I am skipping the negative part because absolute value is removing this. And then a sub n plus 1 factorial will be n plus 1 squared, 2 to the n plus 1. And now we have to be careful because n was multiplied by 2. Now n plus 1 will be multiplied by 2. And the factorial will be applied for the entire expression, which I have to distribute that to 2n plus 2. Okay, let's create a ratio. Ratio test, limit as n goes to the infinity of a n sub n plus 1 over a sub n. You will probably be master with this because I'm like repeating and repeating. Okay, that's me now. Limit at infinity a sub n plus 1. That means I have to copy this. N plus 1 factorial. No, squared, not factorial. N plus 1 squared. 2 to the power of n and 2 to the power of 1. And now that's what I said. 2 times n, 2 times 1. I am distributing and I have 2n plus 2 factorial. Multiplying by the reciprocal. 2n factorial and then n squared 2 to the n. I can definitely see 2 to the n and 2 to the n at the moment. And that's it, okay? Let's keep working. Limit as n goes to the infinity. And I have 2 n plus 1 squared and n squared. And I have 2n factorial, and I have the number 2 more, 2n plus 2 factorial. That means this is my smaller number. I will keep the smaller value, 2n factorial. And this one, I have to kind of match with this. That means I will subtract 2. Yes, I will get the number 2 less, which will be 2n factorial because I'm subtracting 2. And then I have to fill out up to 2n plus 1. That means this will be 2n plus 2. 2n plus 1, 2n plus 2. And n squared was there. Okay, that we can see the quantity 2n plus 1 factorial. I did rewrite as a 2n factorial, 2 number less, and then 1 number less, and the exact number. Okay. Again, it's something like 10 factorial and 12 factorial. 10 factorial and 2 number less will be 10 factorial, and then 11 times 12. Okay? 11 times 12, for example. And I can cancel out. Okay, let's simplify now. You can probably tell me what is this limit, but maybe not yet. Okay, I use the green color. 2n factorial, that was actually the point. And what we have? We do have a limit at infinity of 2 times n plus 1 squared. And then we have 2n plus 1, 2n plus 2, and n squared. Okay, that means what is this limit? We have function n squared, it's 0, thank you, because it's n squared on the top and n to the power of 4. That means definitely denominator is winning 0. 0 is a good number, less than 1. We do have absolute convergence by the ratio test. Okay, I can divide my slide. Okay, it's really good. Okay, that means that's pretty much the ratio test, and I will really suggest you to actually even solve the same questions. Let's try to get the ratio, try to simplify, and then get the limit. Yeah. Okay. The way that you multiply denominator factorial confuses me. Okay, can you be more specific? Which one? You mean 2n plus 2 and this one? Oh, okay. No, it's not, Tino, it's not the concept that you can learn in 5 minutes. I would say an hour. That means you really have to, okay. That means I can explain one more time. If you have 10 factorial and 12 factorial, okay? We have to simplify this. That means the same thing is 2n and 2n plus 2, okay? But let's see this one. I will keep the smaller value, and the bigger value, okay, I can rewrite, I can subtract 2 from 12. That means I will get 10, and I still have to get the product of all of the positive integers from 10 to 12, which is 11, 12. Okay, do you understand this? Is this clear? 12 factorial, it's 10 times 10 factorial times 11 times 12. Yeah, that means I did exactly the same. Of course, we can simplify. Let me add a slide, because my next, I can add a blank slide. That means one more thing, the same thing I will repeat. I will suggest to watch my video about the factorial. Okay, that means you okay with this. Okay, 10 factorial, not 12. Subtracting, and then 11 and 12. 11 times 12. Okay, now what about n factorial and n plus 2? Okay, the same idea. This is n, this is 2 more. That means I will keep the small value, and then I'm subtracting 2. Like, can you see, I did subtract 2 for 10. That means subtracting 2, I'm getting n factorial. And then I have to have n plus 1, n plus 2, because n plus 2 is the last number. 12 is the last number. Make sense? Yeah, can you tell me that this is the second? Yeah, okay, that means this is the first one, this is the second one, and we can simplify, and of course that was the point. And now I can just repeat, because we had 2n factorial, okay, that's what we had, and we had 2n plus 2. Right? That means the same. Even if this is 2n, doesn't matter. I still see a number, and I see a number 2 more. That means this one is smaller. I will keep this one. And I'm subtracting 2 from this, which I will only get 2n factorial, like this one, 10. I did subtract 2. And then I have to subtract 1, and then copy the last number. Okay? You can see 11, 12. That means this is something similar. 2n plus 2 is the last number, like 12 is the last number. 11 was 1 number less. That means this is 1 number less. I did subtract 1, and then I did subtract 2. And of course, we can simplify. It makes sense for the third problem? Yeah, I will, yes, I hope, of course, I don't want to force everybody to say yes. You can still, yes, you can still like look at this again. You can view this video, you can pause the video, and you can digest, because it is quite a concept. I mean, as soon as you get, like everything in mathematics, as soon as you get the concept, it's trivial and simple and trivial, I could say. But if we don't understand, it's, of course, it's always like tricky. Yes, okay, thank you, because I know that the numerical values always helps. Yeah, to figure out, because when we see n, x, abc, it's always difficult, but when we see the numbers, it's easier. Okay, good, I'm happy, because we will have some simplification. Oh yeah, conditional convergent is me. I will find a question, maybe. Okay, let me cover one more test, which is the last test, and maybe, I don't know if I have, but if you can find a test, I mean the series that is conditionally convergent, I can solve it, but if not, I can find something. Okay, I can, yes, because it's always confusing. Okay, let's see. Okay, the last test. Question 3811.6. Yes, I can double check. I can double check the formula, but now, let me check. I'm actually looking at 11.6 section 38. What is 38? Okay, that means it's 1 over okay, we can try to solve this one. Okay, it's actually really good example. Okay, but before that, let's look at the root test. That's what is the root test. Root test has similar conclusion, yes, number less than 1, number greater than 1, or 1. But what we're doing, we're not really computing a limit of the ratio. We're computing a limit of the nth root of the entire formula, a sub n. Okay, that means we have to take the nth root of the absolute value of a sub n. Okay, and if this limit at infinity is less than 1, then we do have absolute convergence. If the limit is greater than 1 or infinity, divergent. If it's exactly 1, it's inconclusive. Okay, that means it doesn't work. Okay, that means similar like conclusion, similar output, but different limit. Okay, and for the root test, I will suggest to apply the root test, especially when the entire formula is taken to the power of n. That means, let's look at this one. We do have quite strange formula, but the entire expression is taken to the power of n. This means that if I will apply the nth root, this will be gone. And then I can only focus on the number inside. Okay? That means that's the only suggestion that I will try to apply the root test, if the entire formula is taken to the power of n. That means, let's see. Root test. we have to compute a limit at infinity of the nth root of absolute value of a sub n. Limit at infinity nth root, and I will copy this, 2n plus 3 over 3n plus 2 to the power of n. And we all know that we can simplify the nth root on the power. Now we do have a limit at infinity only of this expression. And can you tell me what is this limit? Who can tell me this limit? It's less than 1 or greater than 1? It's of course 2/3. And it's less than 1. Perfect. This series is absolutely convergent by the root test. Okay, root test. I can't use the shortcuts RT because the ratio test and the root test will have the same shortcut. Okay, that's we can see. Please always apply the root test when is this case. And I think I have, okay, oh, that's my last one, but I will still solve the conditionally convergent. Okay, yes, we can see nicely we have weird formula, but we do have the n. Actually, I'm just trying to, okay, let's try. That's what we'll do. Root test limit as n goes to the infinity, nth root of absolute value. Limit as n goes to the infinity. Okay, we have a little bit, okay. Nth root of 2 minus 1 to the power of n, and then the nth root. I will actually keep the absolute value just in case, but I think it's because we might know if this is a positive quantity or negative. That means let's keep this absolute value. Okay, the nth root and the power n is gone, and I have a limit of nth root of 2 minus 1. Let's keep the absolute value. And what do you think? What is this limit? Limit at infinity of, I can maybe rewrite like that. Nth root of 2 is 2 to the power of 1 over n. That means what is 1 over n? How expression 1 over n behaves at infinity? It's 0, perfect. 2 to the 0 minus 1. That means what is this number? It's 0, yes. It's simply 0. 0 is a good number. Please remember, 0 is less than 1. This is absolute convergence by the root test. As we can see, the ratio test and the root test are really nice, like really nice tests. I'm really hoping that you will watch this video, maybe even again, okay? And then you will learn the ratio and the root test. Okay, that we got the question. Let me add, because actually you're right, the conditional convergence is always the tricky part. I will add possibly 3 slides, just in case. That means let me solve this one, which will be why you actually pick a good question. Okay. Question, what was the question? 38 in 11.6. And what we have? We do have infinite series, and I don't know if I'm copying this. Let me put, hold on, I think I have, it is alternating one, -1 to the n, ln of n. Is this correct? Please check, because I don't know if my text, I'm actually writing really bad. I think I can just write n ln of n, right? That's what because I'm kind of looking. Okay, that we have to test this infinite series for convergence, for absolute convergence or eventually conditional convergence. That means what I will do. And did you realize I put 3 because we remember all of the problems with natural logarithmic is like, I mean, everything works nicely starting from e. That let's just put 3 Doesn't matter if this is 1, 2, or 3. Okay, that means I see negative 1 to the n. That means I will definitely apply alternating series test. But let's just keep whatever I said, because I said that it's nice and easy to test for the absolute convergence. That means testing the absolute convergence first, because luckily we will get the answer that this infinite series is absolutely convergent. Then the job is done. It's just convergent, absolutely convergent. Okay, but I will test for the absolute convergence, then my formula will change for this. 1 over n, ln of n. Okay, and what do you think? How can we solve this one? Now all of the terms are positive. What test we can use? Because we did change the formula a little bit. I am definitely out of I can't use the alternating anymore, but possibly I will come back. Okay, that's what do you think? What test we can use? Integral test, Odalis. Yes, thank you. I think the integral test works really well. That means what we need. How can I organize? Okay, I will try integral test, of course, just for this one, for the positive. That means I have to know that my function, I can rewrite as x, ln of x. This function is definitely continuous function, positive function, and decreasing. Right? Because in order to use the integral test, I have to check continuous, positive, decreasing. It's definitely on the interval, and let me state from 3 to infinity. Okay, now I can apply the integral from 3 to infinity, x, ln of x, dx. A limit from 3, infinity I will replace with t, and t goes to infinity. And we all know that this is good for the u substitution. I will let u to be ln of x, du is 1 over x dx, which it is in the integral. Okay, let's rewrite. Oh, can I squeeze it here? Actually, I can go here. Limit as t goes to infinity, 1 over u du, and it was 3, now it has to be ln of 3 and nl of t, because that's my limit. Limit as t goes to infinity, integral of 1 over u du is ln of u. And the limits are ln of 3, ln of t. Okay, limit as t goes to the infinity. Let's substitute the upper limit minus the lower limit. Okay, and we can see that ln of t at infinity is infinity. And then another outer function, natural log at infinity, is infinity. That means actually what I'm getting infinity, which means this improper integral is divergent. If the improper integral is divergent, the whole infinite series is divergent too. I can use possibly this color. Divergent by integral test. Okay, that means this is the conclusion that is not absolutely convergent. Okay, that means I can say absolute convergence is gone. Because absolute convergence, we got divergence. That means now, this is important moment, that if the infinite series is not absolutely convergent, could be conditionally convergent. That means what I have to do, I really have to come back to my original formula, and let's see. The original formula is summation from 3 to infinity, negative 1 to the n over n times ln of n. Okay, that's my original one. Let me come back. I did the absolute value, didn't work. Okay, that means it's not absolutely convergent. Now let's look at the original one. That means this is always the most time consuming, because we did the whole job for the absolute convergence and we did get divergence. Okay, that means now I'm coming back to this, and now what test I can use? Just use this formula, not changing anything. What do you think? What will be the best test? Huh? Who can tell me? I know that we still have few. Oh, actually looks like I think the alternating will be the best one, because the ratio test, I think you can try, because you actually right, we have n and we have ln of n. But if we will flip the numbers, we will still get 1. I think all of the functions will be the same. You can, I'm not saying that it's wrong to check, but you can definitely go through and check the ratio. It's still a good choice. Okay, because you can get, but the thing is, by the ratio test, most likely you will probably learn ratio test is not testing for the conditional convergence. That means probably we will get 1 by making a limit of the ratio. We will get the limit will be 1, but it's still worth to check. It's probably like a 2 minutes exercise, and then you will realize, okay, doesn't work. But yes, because we do have -1 to the end, I will try to use alternating series test. Okay, that's what we have. I will pull out the formula b sub n, which is 1 over n ln of n. And this formula is definitely positive. The limit of this formula, it's definitely 0 at infinity, and just denominator is changing. That means this formula is definitely decreasing. We can check the derivative, but we can definitely see that the next term, b sub n plus 1, is definitely less, because if the denominator is greater, the whole fraction is bigger. Okay, that's what we have. We do have really nice check, and check. Then I can say that my infinite series is actually I can say here, the infinite series is convergent by AST. And I don't know if that was said on the yesterday session, but please remember, AST is only testing convergence. If I will not check this free condition, then I will be not able to use the AST. You can't say that the infinite series is divergent by AST. That's not right. Okay, that means please remember, only convergence we have to satisfy. If we're not satisfying one of the conditions, then the test for us is not good. Okay, that means now let's answer the whole question. The absolute value was not convergent. The original series is convergent. Then what we have? We do have a conditional convergence. That means the final answer, I can use, this is conditionally convergent. I can write conditionally convergent. We can write CC, because we can see the original one is convergent, but the absolute value was not. Okay, that means I don't know, but that's actually the really good example, extremely good example. Okay, make sure that you understand every single step in this example. That was a good question. I don't know who. Okay, thank you. Thank you for being with me. This afternoon, the lunchtime. Okay, that means I can finish the session, and we will have a review session. That means I will try to solve as much as possible questions for you, because I really want you to do well. Yeah, Rin, thank you for saying thank you. Yeah, I really like it. Okay, you will hear from me next week.